All right. Hello to our friends joining us via recording. Today we are talking about the integumentary system. The integumentary system is a fancy word for the skin. We are going to focus on the epidermis layer primarily today, and we'll talk more about the dermis layer and below in future classes. I'm going to start off with a little something that my Monday lab friends hopefully can do in their sleep, which they wish they were doing right now, right? Sleeping already. We're going to go through and talk about the types of tissue that are found in the skin, remind ourselves of those things. So the first type of tissue that I see here in my picture on the left, can anyone give me a guess at what kind of tissue we're seeing right here? This first tissue image that we have here? Exactly. Yep. What we are looking at in this picture here is adipose tissue. Remember that the way you identify adipose tissue is we've got these big wide cells. These big wide cells look empty in the middle, but that's because if this tissue was alive, that's where I would find my lipids. So these big open cells, I'm going to type it in the chat for us. Remember that they are called adipocytes. So adipocytes, my fancy word for an adipose cell, that's what we see here, these big, large adipocytes. Remember that adipose tissue is found in that place called the hypodermis, the lowest layer of the skin. And the purpose of adipose tissue, especially when we're talking about it in the skin, is to prevent you from losing heat. It also stores energy, and it's kind of a cushion, if you will, for you. So the first type of tissue in the skin, the deepest kind, adipose loose connective tissue. When we go next door, we are looking at the most superficial kind of tissue now. I'm not going to make you type the entire name of this tissue because it's very long, but let's start with which of the four main tissue types do we see here? So those types are epithelial, connective, muscle, or nervous. Which of those four types do I see here on the right? Can we tell which of the four main types? Epithelial, connective, muscle, or nervous? Yeah, absolutely right. This is an example of epithelial tissue. And our friend Cassidy is going to be a rock star for us and give us the whole name of this tissue. So we've got an epithelial tissue here. This tissue has lots of layers of cells. Each of these little purple dots that you see are each representing cells. And all of this out here is a bunch of cells that are squished on top of each other. So when I'm looking at this kind of tissue, I know it's epithelial tissue because it's pretty much all cells. I know that it's stratified because there are lots of layers of cells. When I look at the outermost layer, the thing called the apical surface, I can see that these cells are really flat or they're really squashed. That makes this squamous. What's special about this kind of tissue, though, is that these squamous cells are completely full of the protein keratin. So let me add that to our chat. Keratin. Keratin is a protein we're going to talk about a lot today. This protein makes our cells really tough, makes them really resistant to damage, and it helps to hold them together. Because all of these cells here on the outside of your skin are completely full of keratin, my special name for what these cells are called, again, some lab review. These cells out here are keratinocytes. Keratinocytes. So over here on the left, we had the adipocytes in adipose tissue, keratinocytes in keratinized, stratified, squamous epithelium. This epithelial tissue that we see here, I told you we see it in the very most superficial layer of the skin. What was the name of the superficial layer of the skin? This one was the hypodermis. What's this region of the skin called here? My most superficial region. Exactly. Yep, this is my epidermis of the skin. So the epidermis layer on the outside of the body, the hypodermis layer down below, very beneath it. Underneath the epidermis, we actually have two other layers of connective tissue. So the layer of connective tissue that I see right underneath the epidermis in this region called the papillary layer of the dermis, the type of tissue that I see here, can you tell me in the chat? Which kind of tissue are we seeing here on the left from my papillary layer of the dermis? Yeah, several of us chiming in. That is an example of areolar loose connective tissue. This is the last kind of tissue that I ask you to know the names of the cells that are inside of it. And the names of the cells that are inside areolar loose connective tissue, they get their name because they build proteins or they build fibers. Do we happen to remember from lab? What's the name of my special kind of cells that are really good at building proteins or building fibers? Yeah, a couple of us chiming in. The name of these cells, these purple spots that are inside of here, these are fibroblasts, fiber builders. Fibroblasts are in any of my kinds of connective tissue that have a bunch of proteins. So I would technically have them over here as well. I just can't see them. And when we're looking at the other kind of tissue that's kind of opposite of this one, dense regular connective tissue, you can see them in there as well. Any kind of tissue that has a lot of protein fibers is going to have those cells called fibroblasts. So areolar loose connective tissue found in the up and down places, those places called the dermal papillae. That's where I find this kind of tissue. That region is very small compared to the region I find this inside of. When I talk about this tissue over here, can you tell me in the chat, and feel free to abbreviate, what kind of tissue do we see over here? My tissue that I find in the reticular layer of the dermis. What do we find over here? My last picture. Exactly. Several of us chiming in to agree. What we see over here, this messy group of pink proteins, this is dense irregular connective tissue. Remember that it's irregular because my proteins are all going in different directions. So some of them are sticking out of your screen straight at you. Some of them are going the same direction as your screen. Some of them are at an angle. That's why it looks so messy. Dense, irregular connective tissue. So when we look at the skin, we ultimately end up with something that's stratified kind of like this, or we have multiple layers like this. So we start on the outside with our keratinized, stratified, squamous epithelium. Then we transition into this small layer right up here at the top, the papillary layer of the dermis, where we have this areolar loose connective tissue. That little small section then is followed by a big section of this dense irregular connective tissue. And finally, we end up at the adipose loose connective tissue down the very farthest. So those are our 4 tissue types that we see in the skin. For my Wednesday lab friends, make sure we're really good at identifying those. I think that my Monday lab friends can attest there are a lot of tissue questions on the exam. So identifying tissues, very important. These ones and our others as well. I got a question in the chat asking about our dense irregular connective tissue. Can anyone help me out? Why do we have dense irregular connective tissue in the body? What is this one good for with those irregularly arranged proteins? Exactly. Yeah, so several of us mentioning when we talk about dense irregular connective tissue, this gives me strength in lots of different directions. I can pull up, down, left, and right. I can pull all different directions and still be strong because this mess of proteins will hold me in any direction. So strength in multiple directions, that's what I use that dense irregular connective tissue for. So we've looked specifically at the different types of tissue found in the regions of the skin, but I want to point out on this picture, the upper part, the outer part of the skin is that epidermis layer on the outside. Then we've got this really small papillary layer of the dermis up at the top, the much larger reticular layer of the dermis, and then the hypodermis down underneath all of that. Hey, a quick review for my Wednesday lab friends especially. There are two major kind of glands that we see in the skin. One of them I see right here attached to my hairs. One of them I see that goes straight to the surface of the skin. Would it be number one over here or number two over here? Which of these is called a sebaceous gland? One or two? Which of those is the sebaceous gland? Exactly. Yeah, several of us chiming in. Sebaceous gland is number one. Sebaceous glands dump sebum. They dump oil onto your hairs. That takes it up to the surface of the skin where it waterproofs your skin. Over here, we have a type of gland called an eccrine gland. Eccrine glands don't make oil, they make watery stuff. So my eccrine gland that I see here dumps the watery sweat onto the surface of the skin, keeping your skin moisturized. A couple other things I'll point out. Up here at the top, we can see those things called free nerve endings. Can you remind me in the chat, when we talk about free nerve endings, do you remember what those help us to do? We couldn't really see them on our models, but we did talk about what they do, at least briefly. Yeah, exactly. So Jessica and several others chiming in, this is how we feel pain in the skin. This is also where we feel sensations like tickling or itching when we get a mosquito bite, is these guys here, the free nerve endings. Down much lower in the skin are my receptors called the lamellar corpuscles. Lamellar because they're laminated. They've got all these layers of tissue around them. Remember that the lamellar corpuscles detect pressure. What we can't see on our picture here are the ones that I'd find up really high. So those ones called the tactile corpuscles, they're not seen in this particular picture, but remember that those were up here in the dermal papillae and they helped with touch sensations. So lots of different structures that we find, almost all of them in the dermis layer of the skin. For today's class though, we're really going to focus on the epidermis layer, the layer here on the outside. When we talk about the epidermis layer, one of the first things, one of the most important things about the epidermis is that we have the protein keratin inside the cells that live in the epidermis. So the keratin protein is what fills up all the cells in stratum corneum. My cells starting from stratum basal and all the way up, all of them make keratin. Keratin is a protein that makes your cells really strong and really resistant to damage. So let's look at the structure of keratin to figure out how it makes your cells strong. Hey, over here on the left, I'm looking up close and personal at a keratin protein, and I'm looking at a structure called an alpha helix. Now, it's been a minute since we talked about protein structure. Let's see if we can remember this. When we talk about an alpha helix, which level of protein structure are we talking about? Which level is those alpha helices and those beta sheets? Exactly. Yep. Alpha helices and beta sheets are an example of secondary structure. So when I look up close at the keratin protein, notice that I see this curly Q pattern, or my alpha helix, that makes up the keratin protein. That by itself is not really notable. A lot of our proteins have alpha helices, but here's what I need you to underline, highlight, star when you're looking at this picture here. This line right here. Hydrophobic. Hydrophobic. I need us to underline, highlight, star that there's this red strip that I see right here that's made up of amino acids that are hydrophobic. Remind me in the chat, if I'm hydrophobic, how do I feel about water? If I'm hydrophobic, how do I feel about water? Exactly. I do not play nice with water. I hate it. I don't like it. I'm afraid of it. Whatever we want to say. Water is not my jam. So we take this keratin protein, got a long stream of amino acids, and we curl up that keratin protein. And now we've got a strip where the whole side of this protein doesn't like water. Well, this side of the protein chain doesn't like water. And meanwhile, its next door neighbor has a strip of the protein chain that also doesn't like water. So remember when we were talking about those things called hydrophobic attractions, where two things that are hydrophobic squeeze together. They don't want water to be around them. Well, that's what's going on here in the keratin protein. One part of the amino acid chain has a strip that doesn't like water. The neighboring part has a strip that doesn't like water. If they curl around each other, we can squeeze all the water out. So when we look at the keratin protein up really close, part of what makes it so strong is that it looks like the Twizzler, like we see over here. We twirl together the parts of our protein chain close together. And when they're close together, they're really strong. Hey, by the way, I am looking at my 3D shape of the protein now over here, where I had two alpha helices that rotated around each other to build this shape. What is the description of, or what level of structure is the 3D shape of a protein? What level of structure is my Twizzler that I see over here? Remember? Yeah, several of us chiming in. The 3D shape of a protein is called its tertiary structure. And remember, all the proteins in your body have a 3D shape, but not all of them have what's called quaternary structure. Remember, for me to have quaternary structure, there has to be more than one amino acid chain that's interacting with each other. So when we look at some of our proteins, they like to build themselves out of lots of pieces. Some of them just like to be one piece. And if I just have one piece, I only go as high as tertiary structure. So let's recap what we've said so far. We have said that keratin is a really strong protein. What makes it so strong is the fact that its tertiary structure has these amino acid chains tightly curled around one another. Keratin, a strong protein that makes my skin cells really strong. The other thing that keratin does is it helps us to build a kind of connection point between the layers of the skin called desmosomes. So when you think of desmosomes, I want you to think of keratin proteins. If you've ever paid attention when you go into Walmart or a big store like that, if you look up at the ceiling, a lot of times you'll see the little rafters coming down the ceiling. Those rafters help to hold it up. That's what keratin proteins do when we're talking about this kind of junction called a desmosome. The goal of desmosomes is to hold cells together really tightly to make sure they don't get pulled apart. So what I do is I put keratin proteins at all kinds of different angles in my two cells. That way, let me get my pen here. That way, if this cell starts getting pulled away this direction, the neighboring cell says, oh, I got you. You're attached with these keratin proteins down here. Or if this cell starts getting pulled this direction, I've got a bunch of keratin proteins over here that are attaching it. Desmosomes are really good at giving me a strong attachment point no matter what direction I'm being pulled. Now, desmosomes, this kind of cell junction, you can actually kind of see it depending on how good your microscope is. If you remember, we had that layer of the skin where I told you that if you look really closely, It almost looks like the cells have spines on them. Does anyone remember the stratum or the layer of the skin that I told you looked like it kind of had spines? And its name totally comes from those spines that are on the cells. Exactly. Yep. Dr. Allis is making you type not English words. Dr. Allis is being mean. Stratum spinosum is that big layer of the epidermis where the cells are still alive and they're attached to each other really strongly. They're attached really strong because they have these desmosomes. So the name stratum spinosum actually comes from these desmosomes, these type of attachment sites that you can pull up and down and across, and they're not going to let go because we have those proteins anchoring us in all of the directions. Desmosomes. In addition to strong attachment sites in the skin, because that's what desmosomes are, they're strong, we also have a type of junction in our skin that helps to waterproof us. And that junction is called a tight junction. Now, I need everybody to write down something for me. I asked my morning class, I think we're on page 3. Is that accurate? When we start talking about tight junctions, is that page 3 of your notes? Tight junctions? Yes. Okay. So on page 3, somewhere next to these word tight junctions, I need you to write that there's no keratin. Up to this point, we've talked a lot about keratin. We've talked about how it makes the cells strong. We've talked about how it helps them to build desmosomes. When we're talking about tight junctions, we're not talking about keratin proteins anymore. We're talking about a different kind of proteins. I'm not going to go into the specifics of this different kind of proteins, but what I do want you to know is that they're not keratin. Tight junctions also don't have the same function as desmosomes do. Desmosomes are really good at pulling in all kinds of directions. When I talk about tight junctions, it's not that they're particularly strong, but what they are is they're really tight. We are essentially fusing together the plasma membranes of neighboring cells. So tight junctions bring the membranes together tightly. They help to prevent any water that's out here from getting in between the cells down to inside your body. So tight junctions help to waterproof our skin. They fuse together the membranes and they don't come apart. Desmosomes, if you notice in my picture down here, oops, I lost my pen. My picture down here, you can see that there's actually space in between the membranes when we're connected with a desmosome. Desmosomes are not going to waterproof you, but they're going to make you held together really strong. So remind me again in the chat, tight junctions, they do or don't use keratin. Is there keratin in my tight junctions? Correct. There is no keratin. We do not use keratin to build tight junctions. We do use it to build desmosomes. We do use it to make our cells strong, but we do not put it in tight junctions. So one way our skin is held together tightly, one way we're waterproofed, is using these tight junctions. The other way that your skin is waterproofed is because of some things called glycolipids. When we talk about glycolipids, their name tells me about their structure. At the top, they've got a sugar. That's where glyco means sugar. And at the bottom, they've got these lipid tails. These lipid tails are just like the lipid tails on the phospholipids of the plasma membrane. Remind me in the chat, the tails of our phospholipids, they did or did not like water. The tails of my phospholipids, those things that make up the plasma membrane, we do or don't like water. Yeah, we do not like water. Accurate. Lipids in general don't like water, and that's totally true still, even of glycolipids. So glycolipids have another name. I'm going to type it here in the chat. The other name for my glycolipids is lamellar granules. Lamellar granules, as in stratum granulosum. The layer of your skin where we start to do waterproofing with glycolipids is the layer called stratum granulosum. So the way these things work is cells in stratum granulosum build them, and then they spit them out on the outside of them. Think of stratum, or think of these glycolipids kind of like a raincoat. So any water that tries to sneak in from outside the body, it's going to bump into this raincoat and it's not going to be able to get through. So stratum granulosum makes these lamellar granules, makes these glycolipids to prevent water from coming in. But the unfortunate problem is we also prevent water that comes from this way. The water that comes from this way started as plasma, and there's a couple of things in your blood's plasma that cells kind of want to make sure they have. Any ideas of what might be inside your blood that cells in your body want? There's a couple of things. What do we think our cells might want that floats around in blood? Yeah, so the blood cells are erythrocytes. Yeah, the erythrocytes are transporting oxygen. So one of the things that we want to have is oxygen. The other thing we want to have, like Hayden and Jessica mentioned for us, we also want to have glucose. We want to have our favorite food. Glucose and oxygen both travel throughout the body using that liquid to get throughout the body. When I put on my raincoat, it's going to block any water and dissolved stuff from getting in. That's perfect. But it's also going to block any water or dissolved stuff from going out, which means I'm literally going to starve to death. Stratum granulosum is the layer of your skin where the cells first start to die. They're dying because the oxygen and the nutrients that came from my blood vessels down here, I'm blocking them. I'm waterproofed. They're not getting in. So in stratum granulosum, we make these things that make us waterproofed, which is great from the outside, but ultimately it's going to end up killing us. So glycolipids, really important for waterproofing, but also the reason that the cells in this layer and above, everybody's dead. Hey, this particular image of skin that I see right here, I've got 1, 2, 3, and 4 strata, 4 layers in this skin. Am I looking at thin skin or thick skin? Since I have 4 layers in this skin. Yeah, several of us chiming in. I am looking at thin skin. Thin skin only has 4 layers. When we talk about thick skin, not only is stratum corneum bigger, but we also add in an extra layer right here. I add in that clear layer called stratum lucidum. Stratum lucidum. Remember that that is only seen when we're looking at thick skin. I'll never have that in thin skin. By the way, I realized that I didn't teach you all this in lab, and I probably should. One way, and it's a little late for my Monday lab friends, I apologize. One way to remember the order of the strata in the skin, come, let's get sunburned. Come, let's get sunburned. Stratum corneum, stratum lucidum, stratum granulosum, spinosum, basal. There are lots of different mnemonics out there. That's the one that I like. If we're talking about thin skin, it would just be come get sunburned, which I like to joke with students. That's what the sign outside of NRH2O should say. Come get sunburned, because that's what we do when we go there. We get sunburned. Actually, Dr. Allis has one of those swim shirts because I'm so fair-skinned. I need something to protect me from the sun. So come, let's get sunburned, or whatever else you found to help you remember from stratum corneum to stratum basale. I've talked a whole bunch. I need to pause for a moment. What questions do we have? Or shoot me an emoji. If you're doing all right, shoot me an emoji. If you can think of a question, add that to the chat for me. All right, getting some smiles. Light bulb moment for Callie. Love it. Two-thirds of us are sleeping, right? All right, well, if we think of some other questions as we continue on, please always feel free to put them in the chat. I promise I'm going to keep looking over there as we keep working our way through. So, keratin makes our cells strong, connects them to each other tightly. Tight junctions squeeze the membranes together so no water can get through. Glycolipids cover the cells, again, to make sure that no water can get through. There's one other molecule that we have in the skin, or in the epidermis of the skin, that helps to protect us. And that last molecule that helps to protect us is melanin. So the last protective molecule in your skin, the protein called melanin. So melanin is made by the weird looking cells that we see right here. These cells are called melanocytes. So melanocytes are the only kind of cells in your epidermis that can build melanin. We have very few melanocytes compared to how many keratinocytes we have, which means that our melanocytes have to be able to reach up in between those keratinocytes and share the melanin that they need. See, melanin is really good at absorbing UV radiation. UV radiation likes to damage your DNA. So we don't want that happening. We're going to use melanin like an umbrella over the DNA of all your different cells. Here's a fun fact that I need all of us to write down somewhere in our notes. So you should see this picture in your notes. If we were in the lecture classroom together, we'd take a moment and we'd look around and notice that there are a lot of different skin tones represented in our classroom, represented in our world. When we look at all of these different skin tones, the interesting fact is that all of us have the same number of melanocytes. All of us have the same number of these cells. So we all have the same potential to build melanin. Some of us build a lot of that protective melanin. Some of us, like Dr. Allis, don't build so much. It's not the number of melanocytes that you have that determines whether or not you're building a lot of melanin. Instead, it's the activity of your melanocytes. So Dr. Allis's melanocytes, Dr. Allis is down here on the very fair end of the spectrum. My melanocytes are super lazy and they do not make me much melanin. They just don't care. As your skin tone gets darker, your melanocytes are making you more melanin. But again, everyone has the same number of melanin builders. It's just they don't all work at the same rate. Remember from last week when we were talking about gene expression, so taking the directions and turning it into a protein, we all have the same directions. It's just some of us read them and use them more than others. Dr. Allis is having a moment. Oh, I was like, what else am I supposed to tell you? The other thing I'm supposed to tell you is the way that we can increase the amount of melanin in our skin. So it's possible for you to purposefully expose your skin to UV radiation, you know, that stuff that can change your DNA. It's possible for us to expose our skin to that. When that happens, my melanocytes freak out and say, oh my gosh, we need more melanin. Gotta make more melanin. So when we expose ourselves to UV radiation for the purpose of making more melanin, we're doing something called tanning. So tanning, as in what you do when you lay in a tanning bed, or when you lay next to the pool, or when you're out in the backyard, wherever you are. When we purposefully expose our skin to UV radiation, our melanocytes are going to kick into gear. They're going to make us more melanin. Now, at the same time, we have to recognize that we're exposing our skin to something that we know has the ability to damage our DNA. So I know how much it's amazing to be a bronzed god or goddess, to have that great amount of melanin, but to get that amount of melanin, to up the amount of melanin, to get tan, we're taking a risk, exposing ourselves to that UV radiation. And I know Dr. Allis is on a little bit of a soapbox here, but for quite a while, I actually worked for a skin cancer dermatologist, and we spent like 3 days a week cutting off skin cancers. So Dr. Allis is a little bit passionate about tanning and about skin cancer. We'll talk a little bit more about the types of skin cancer here in a moment. But when we think about tanning, here's a funny cartoon that I pulled just for you all. So we've got a keratinocyte on the left talking to a melanocyte on the right. The keratinocyte says, "What's wrong, melanocyte?" And the melanocyte says, "She's tanning again." So don't make your melanocytes cry. Don't expose them to UV radiation. Yes, it will make them make more melanin, but it also has the potential to give you skin cancer. Not ideal. Yeah, and Lisa's totally right. The more tanning we do too, the more UV radiation you expose your skin to, the older and more aged it makes you look. This morning I found a really awesome GIF. I'm not sure if I'm going to be able to find it again. I am. Here it is. Oh no, that's not the right one, but it's the right person. So I'm gonna pop here in the chat. This person here, she has the moniker from social media of Tanning Mom. As you can see, Tanning Mom loves to go tanning. Tanning Mom got into big trouble when she took her, I think it was 5-year-old child with her to go tanning, and her child got very, very burned. So don't be like Tanning Mom. Don't make your melanocytes cry, and definitely do not take your children with you when you go to the tanning beds, which hopefully we're not going to do that anymore. Dr. Allis will now step off of her soapbox for you. So Victor asked an interesting question. Victor asked about spray tans. I actually kind of want to put that question to the class. Yeah, so Lisa's thinking it's okay. What else are we thinking? Why or why not would that be okay? I would love to hear some opinions. Yeah, so Jessica's mentioning spray tan is a dye. Yeah, you can sometimes use it as a lotion, lotioning it in. Yeah, so and Lisa's mentioning, as long as those chemicals aren't icky. Yeah, they're not bad for you chemicals. In general, with the spray tans or the lotion tans, you're adding pigment from the outside of your body. So it's not that we're making our melanocytes make more melanin for us. It's that we're adding something to our skin cells to make them look darker. So like Samantha mentioned, I love it. She mentioned that we're not being exposed to UV rays when we do spray tans. UV rays are the problem. So if we're not being exposed to UV rays and we still have a way to get a little bit darker, that is far preferable to using those UV rays, those cancerous UV rays, to change our color. Yeah, so Han mentioned that it can make your skin dry. Yeah, so that's the deal with things like spray tans or certain lotions that are attaching to the cells in your skin. They are playing around with the chemistry of those cells too. So that's the trade-off. If we might get a little bit dry, but if it prevents skin cancer, Dr. Ollis is all about that. But yeah, great question. If you want to be tan, please do the spray tan. Please do not do the side of the pool tan. All right. Thank you for tolerating my soapbox. I appreciate it. Let's talk about what happens if you don't have any melanin. So we're looking at some pictures from a condition here called albinism. Individuals with albinism have melanocytes, but their gene for the melanin protein is mutated. So they cannot build the melanin protein. So you can see from these pictures, and these are actual pictures, by the way. This is not people wearing makeup. These are actual individuals with albinism. Anywhere that we would have had the melanin protein is now clear, or it's translucent. So melanin not only helps us with our skin color, it also dictates our hair color, as we can see here. And it also plays a role in determining our eye color. So in individuals with albinism, we have no melanin anywhere. Yeah, I agree. Lisa mentioned that this is beautiful. I agree. I love these pictures as well because they highlight for us that albinism can happen to anybody. It's not just one particular race of people that can be impacted by it. Anybody who has a mutated melanin gene can be susceptible or can inherit albinism. When we talk about albinism, why do you think that this disease is so dangerous? For individuals with albinism, they don't have melanin. Why would that be dangerous for them to have no melanin? Exactly. Yeah, so several of us are mentioning correctly, melanin's job is to protect you from UV radiation. If I have no melanin, I have no protection from UV radiation. So I must have melanin to keep me safe. Yeah, Sam's mentioning she has a friend who can't go outside very often because she has albinism. Yeah, absolutely true. Individuals with albinism, if they're going to be outside, they're typically completely covered in UV blocking clothing, in sunscreens that block UV waves. They have to be very careful because, like you and I have at least some level of melanin to block some of that UV radiation. They have none. So yeah, they can absolutely get burned, like Hyan mentioned. There's one other condition that UV radiation can cause. What else do we think that individuals with albinism would be more likely to get? Any thoughts? Exactly. Yeah. Individuals with albinism, part of why they have to avoid being outside is because they're at such a higher risk of skin cancer. Yeah, so Hayden mentioned as well, a couple of us are mentioning issues with vision. Great connection to make. Our very last week in lab, we're actually going to dissect an eyeball, and we'll see inside that eyeball there's actually melanin inside there as well. The job of the melanin is to protect the nervous tissue cells that detect light. So if we don't have that melanin in there, those cells could get damaged as well. So skin cancer, primarily what we're going to talk about, but it's a great connection to make too, that we can't have eye problems because inside the eye is another place we find melanin. The last thing I want to talk with you about today is the types of skin cancer that we can develop. The types of skin cancer that we can develop are named based on which layer, which stratum of the skin the cells originate in that become cancerous. So the very bottom layer of the skin, remember we talked about is stratum basal. If UV radiation damages one of the cells here in stratum basal, that cell can turn into a basal cell carcinoma. So if the cancer starts in stratum basal, that becomes a basal cell carcinoma. Basal cell carcinomas are the most common kind of skin cancer, but they're also the least deadly of the skin cancers. When we talk about basal cell carcinoma, they're relatively slow growing, but perhaps what's more important about the basal cell carcinoma is the way that they grow. So see how here at the bottom of my basal cell carcinoma tumor, I've got this kind of straight line of cells. That means it's going to be easier for me to catch all of the cancerous cells that are growing in the skin when I'm trying to remove them. So that skin cancer dermatologist that I told you all I worked for, we did this thing called Mohs surgery, where what we do is go in and take a chunk of tissue around the tumor. We'd send it to our histologist. He would look at it and say, yep, you got all the cancer cells, or no, you didn't. Okay, we didn't get them all. So we go in and we take another chunk. Okay, send it to the histologist. The histologist looks to see, did we get them all? No, we still didn't. So we go down one more time. And because all of those cancer cells grow in this uniform pattern, it's easier for us to just take the cancer tissue, as opposed to what we see over here. Notice how the way that a squamous cell carcinoma grows, it's not growing all down at the same rate. I've got these little tendrils or these little groups of cells just kind of snake their way down. It makes it harder for me to catch all of those cells that are inside that tissue. Squamous cell carcinoma happens when we have cells from stratum spinosum that become cancerous. So when we talk about the cells from stratum spinosum, they're called squamous cells. So again, those cells don't grow down as nicely, as uniformly. They're a little bit harder for us to catch with like that Mohs micrographic surgery. Oh, nice. Cassidy mentioned that her dad actually just recently had that. Yeah, so Mohs surgery, a very common way to deal with these two types of skin cancer, squamous cell and basal cell. We can do the Mohs surgery for. Melanoma is its own beast. Melanoma is the most serious kind of skin cancer. I believe it is also the most rare as well, which is good for us. When we talk about melanoma, this kind of skin cancer develops because my melanocytes, my melanin producing cells, they got mutated. And when they got mutated, they start to divide very rapidly. And the thing with melanoma is that it goes down very far into the dermis very quickly. And it's also irregular, like we saw with the squamous cell carcinoma. So melanoma, the most likely, let me give you a cancer word here, to metastasize, meaning it's most likely to leave the skin and go to other places in the body. So during our class on Wednesday, we'll talk about how you stage melanoma. We stage it based on how many layers of the skin or how many places in the body it's traveled to. If it's traveled to a bunch of other places in the body, that's bad news for us. We want to catch it as soon as possible so that it doesn't spread and we have to treat tumors in more than one place. So when we look at these different types of tumors, they look different from one another because of the way that the cells grow. I want to point out, hone in on this one right here. Notice how we see a cancerous growth here that's very dark in color. The reason it's so dark in color is because the cells that are making this cancerous tumor are my cells that make melanin. They're my cells that normally build my skin pigment. So if my skin pigment cells become cancerous, they're going to keep making melanin, and we'll see this really dark tumor that we see here. Any questions about my types of skin cancer, albinism, melanin, anything like that? Or shoot me a thumbs up if we're feeling good. Perfect. Getting several thumbs up. Okay. Well, I'm going to call that a day, but if you think of questions as you're working on this content, Please feel free to reach out via email. I'm happy to help you with those. Wednesday lab friends, remember that we need to be on campus a little bit early so that I can get us into the lab, try to get that exam started right on time. So Wednesday lab friends, good luck with the rest of your preparations. Monday lab friends, take a breather, take a little bit of time off, celebrate the fact that the midterm's done, then get back down to business. I'll make sure that I'm releasing some of those future weeks of lab and lecture for you so you can keep working on that stuff. So have a great afternoon. I will stick around and chat if you have any other questions for me.